Good morning, everybody. So today I'm going to be talking about how to take some of the stuff we've just learned with those deviations, and then we talk about standard deviations, and we're going to create something today pretty darn cool called z-scores. Now, z-scores are pretty cool for a lot of reasons, but let's do a quick reminder of ourselves. Let's bring us up to speed. I know it's easy to forget some of that stuff. So I'm gonna go back and just remind us what we've already done. We've done this material, so this should be just getting your brain fresh and clear so that it's ready for the new material. Okay. So remember when we were talking about getting a measure of variability. Okay, so here was our example with the Brady Bunch. Kids eating the pancakes at the pancake buffet, and remember there were 6 children, and the first kid ate 8 pancakes, the second one 7, the third 9, etc. And so you recall, okay, put them all together. Sum of x is 36, divided by the number of kids. 6 of them, the average is 6. And so you remember, it was like, okay, let's just say you just pick one of these kids at random and guess how many pancakes are in. Well, 6. Oh, yeah, it's the best guess you got, right? Any other guess, and there would be more mistake going on. Okay, so how much mistake would you make if you guessed 6, right? That's kind of what we're getting at. So in order to do this, what we could do is figure out these deviation scores. And recall these deviation scores, x minus x bar. And in these deviation scores, it must always sum to 0, right? I mean, we've hopefully gotten that one beat into our heads. If it doesn't sum to 0, you screwed up somewhere, right? So the sum of the deviations must always be 0. And again, these deviations, by the way, are like mistakes. Let's say the first kid, you guessed a mean of 6 pancakes. Oh, I guess 6. You're wrong by 2. All right. The second kid, oh, I guess 6. You're wrong by 1. Okay. So that's what I mean by the error there. Okay. So because it adds to 0, and we want to get like the average error or something like that, you can't average 0, right? And then it's always 0. So you remember what we did was we squared them. Okay. So hopefully this is a familiar idea. We took each of those deviation scores, right? So the first kid actually ate 8 pancakes. The mean was 6, so x minus x bar, right? 8 minus 6 equals positive 2. And so in the third column, we're going to square those deviations. So now that we've squared them, they must all be positive, right? Must all be positive. And so we call this column sums of squares. Remember, SS, or sum of the squared deviations from the mean. So if you add them all together, you get 28. All right, very cool. So that's the average squared deviation. You recall what happens is that, oh, there you go, the full name. I just said that. Ha, we knew that. So that's the sums of the squared deviations from the mean. Okay? You recall if I take the average of the sums of squares, right, sums of squares over n, and you get 4.67, and we call that the variance, right? S squared sub x. All right. And so, as you recall, hopefully now from all of our equations, the variance in and of itself is a useless in this up until it's still useless. Okay, it's still, I mean, it's important to know because we most certainly will be coming back to it over and over and over. But it's like the average squared error or some nonsense like that. It's like, what the hell is an average squared error? So if it's squared error, obviously the next step is to take the square root of it, right? And so 2.16, the standard deviation, in a lot of ways, like if I just said 6 as my guess for how many pancakes each kid ate, the average mistake would be 2.16. I mean, that's just, generically what we're looking at here. So the standard deviation, the average distance that each score is from the mean, something of that nature. Okay? So now hopefully you recall this particular slide right here. And this was your handout, right? So what we just discussed was the definitional formulas on the left column. And they made sense because, I mean, sum of x minus x bar squared makes sense when you're talking about deviations and everything else. Whereas on the right column, if you recall, were the computational equations, right? And so if you went back to the Brady kids and you did that stuff, it would be simple enough. You could get the exact same answer. With with the computational equations. Okay, so we're hopefully kind of up to par on deviations. You sum them, you get 0. If you square them, you get the standard deviation. Well, the standard deviation is going to be a very, very critical concept in z-scores, because what's going to happen is that each standard deviation is going to equal 1 unit on a z-score. So take a look here. Here's a distribution, normal distribution, and in this normal distribution, the mean is 80, right there at the center. It's got a standard deviation of 5. And so you see what happens is that in this distribution, I'm going to put the score of 80 in the center, and then 5 units over to the right, that is plus 1 standard deviation. That's what they're saying. This is 1 standard deviation from the mean, whereas the 75, which is, 5 units below the mean, is minus 1 standard deviation. Now, as we move forward, these 3 points here, right? What we find, in fact, at the 80, you could even put 0 standard deviations from the mean, right? Something like that. And so later on, these are going to be z-score of -1, z-score of 0, z-score of +1. Okay, so in just a few more slides, instead of calling it, 1 standard deviation above the mean, 1 standard deviation below the mean, we're going to give them names z-scores. Z-score of -1, 0, +1 on these 3 spots. Okay, very cool. Because normal, here, why do we want to know about z-scores? Raw scores are meaningless, right? I mean, I scored a 79. Yeah, what? Who cares? What's a 79? And so what happens is that it becomes very difficult to work with. But when we get to z-scores, if you're like, I had a z-score of plus 1.6, and that stands all by itself. I don't need to care what the mean was. I don't need the mean of z-scores will always be 0. So if you tell me you have a z-score of positive 1.6, you're like, well, my score is higher than the average, higher than the mean, and quite a bit so, And so I know a lot of information about your score just knowing that z-score. It allows us to calculate a person's relative standing. Yeah, I mean, as I said, you're positive 1.6, you're above the mean, and you're way above the mean. But if I said my raw score is 79, you're like, so what? What is that? I don't get it. But without even having to deal with a frame of reference, a z-score of plus 1.6 tells me very many things. And with z-scores, you can compare different things. You can compare apples and oranges. Things that are radically different from each other can be compared using z-scores. So, what do I got here? Yeah, wait, where is it? Here. Yeah, here. All right, there it is. So the standard normal curve always is centered at 0 and is divided up so that it's, a z-score of 1 is 1 standard deviation above the mean. A z-score of 2 is 2 standard deviations above the mean. A z-score of 3 is 3 standard deviations above the mean. So going back to this image, which was the mean of 80 and a z-score, a standard deviation of 5, we put these 3 critical points of, -1, 0, and +1. Well, guess what? +2. +2 would correspond to a raw score of 2 standard deviations above the mean, 90. And a z-score of -2 would equal 2 standard deviations below the mean, or 70. Okay? And so we find that no matter what the raw scores are, it's got a mean of 80 and a standard deviation of 5. I don't care what the mean and the standard deviation are. Once we turn it into z-scores, it will always look like this image right here. Always. Okay? And because of this property, I can compare what you got on an English test and a math test, even though one had an average of 26 and the other had an average of 94. It just doesn't matter. It's irrelevant once we convert things to z-scores. So, and by the way, when it comes to these z-scores, it doesn't matter if you're using scores from a sample or from a population. Okay, it doesn't matter if you know in the top equation. Look, you've got the population mu and the population sigma, or mean and standard deviation. And in the bottom, you've got the sample mean and the sample standard deviation. So it's absolutely irrelevant if we're talking samples or populations, okay? It's just the exact same equation. And so if you want to calculate a z-score, what you need to do is x equals the score you're interested in, okay? I got a 97. Okay, what was the average? Oh, the average was 84. Okay, so it's 97 minus 84. What was the standard deviation of this? Oh, 14, And so you just put these three numbers in and solve it. We're going to do a bunch of examples here, but it's really simple. If you know the mean and the standard deviation, you can then calculate a z-score for any outcome, okay? Z-scores produced from z-scores produced from different sources can be compared directly. Right, if you scored a 32 on an English test and a 73 on a math test, you just can't compare them. But if you put them together, I already said this stuff, so I don't know. Here it is. Okay, now if you have your z-score and you would like to go backwards, okay, and again, look, there's two equations here, but notice they're the same equations. One has just got population parameters in it, one has got sample statistics in it, but they are the same equation. So if you know a z-score and you want to bring it back to the raw score, take a look. You would take, I'm looking at the bottom formula here, so you would take the sample mean, and you would add the z-score times the standard deviation. And if you calculate that, you'll end up with the original raw score that created that z-score. Okay, we're going to do some examples, like definitely some examples. So no problems here. Oh, I just did that one. This one. And so here, any normally distributed data can be converted to the z-scores. Okay, as we said, the mean, in this case, the average is 50, the standard deviation is 10. And therefore, a raw score of 50 will always, the mean of your distribution of raw scores will always correspond to a z-score of 0, always. Look at that, it's got a standard deviation of 10, therefore, look at that, 10 raw score units will correspond to 1 z-score unit. 10 below, minus 1. And so, lo and behold, it maps out nice and pretty. Oh, here. I'm all the way down here. I see. Okay. So, again, this is a probability distribution. Don't forget that. And so, in fact, you see here what I've got. Wait a minute. Where is it? Hey, I just moved off the screen. Oh, it's so clever there, wasn't it? There. Okay, so take a look here. It's a probability distribution, and so take a look on the left side. Again, I'm not going to be putting that little frequency on the left side. It's not going to be put there when I draw these things. But never forget that the height of that curve represents the frequency of that score. Okay, so there's always an F on the side there for frequency. Okay, so we can put percentiles, and what's beautiful is we are going to find that every single point in the z-score distribution is known. Okay, and we're going to be working with your statistical tables. I hope you have them. Okay, if you cannot find your statistical tables, pause. They are posted on Blackboard. You can find them, but hopefully you can have them right now. Okay, we're going to be coming to this. So what we have is, I mean, just like we said earlier, with frequency distributions, you can compute percentiles, right? Percent of scores falling below or something of this nature. Okay, now here is a summarization of the two equations that we've already talked about. Okay, on the top here, this little one, z equals x minus x bar over s sub x. Okay, we've seen that equation, we talked about it, we're going to work with it. You go down to the bottom far right, x equals x bar plus z times sigma. Okay, and so guess what? We talked about that one as well. Okay, so here's the deal. If I know a raw score, okay? I can convert it to a z-score, and if I have a z-score, I can take that z-score, look it up in a table, right? And we're gonna be learning how, and to bring a percentile out. Awesome. But this works in the other direction as well. If I know somebody's percentile, oh, I scored in the 84th percentile, okay? I can go to the z-score table, look it up, find out what z-score is the 84th percentile, and then under my face, once I have found the z-score from the table, I can then convert it back to a raw score. Okay? So raw scores can be turned into percentiles. Percentiles can be converted into raw scores, but in both cases you must get z-scores in between these two processes. Got it? Okay. So here's an interesting example. We're going to compare apples and oranges. Okay? I mean, that's what we're going to do. Okay. I went to the cafeteria the other day with $1. Piece of fruit costs exactly $1. I can buy one piece of fruit, and I am a cheapskate. I want the best value. Okay? So I found two pieces of fruit, an orange that weighs 9 ounces and an apple that weighs 9 ounces. Now, it's the same size fruit, but you know what? I am such a cheapskate. I want to get the best bang for my buck, okay? I want to know which is the more outstanding fruit. Which one is a better value for my dollar, okay? So what I'm going to do is I'm going to calculate the z-scores, okay? So imagine I know this information. I know it's a little bit weird, imagine, but you know, you can imagine. So imagine we know that apples weigh 6 ounces on average and with a standard deviation of 1.5 ounces, okay? So take these pieces of information, okay? Now, go to the top left corner. Z equals x minus mu divided by sigma sub x, okay? As we said, mu is 6. That is a given to us. The sigma is 1.5. Okay, I've got those two pieces of information. And the apple that I have picked in the cafeteria is 9 ounces. So 9 minus 6 over 1.5. So that's 3 over 1.5, or positive 2. In other words, if you take a look at my distribution, my apple falls way out there. You see this distribution centered at 6 ounces with one standard deviation above, two standard. And so what we find is I have a large apple, and it is not a common occurrence. Okay? Let's take a look at this orange. Okay? Oranges weigh an average of 10 ounces with a standard deviation of 2 ounces. Okay? And so, again, we're going to take the pieces of information and put it into the equation and say, my orange that I picked was 9 ounces minus the average weight of oranges, which is 10, divided by the standard deviation, which is 2, and you get a negative 0.5. And so what we find is that I can, first off, I can just compare these two things without even doing anything else. And I can say, check it out. Since the apple had a z-score of positive 2, it is by definition more outstanding than the orange, which has a z-score of negative 0.5, right? Positive is bigger than negative, okay? But let's take a look here, okay? I can put the two together onto a single distribution now, because now that I have z-scores, I do not care that oranges had a different mean than apples. It is irrelevant once I have z-scores. And so in the world of z-scores, it's quite clear that apples are larger than oranges, and apples are fairly infrequent, and the 9-ounce apple is fairly infrequent. A 9-ounce orange is less than average, but still pretty common, okay? So now here's what we're going to do. This is kind of weird. I want you to go find your charts, okay? You know those charts. And there they are. Okay, now I apologize. I don't know what to say. These are tiny little numbers on here. But what's going to happen in the z-score chart is that what you've got here is when you want to look up a z-score, you need to look up down the left side first, and then across the top second. So in our first case, we have found that the apple has a z-score of positive 2, okay, 2.0. And so what you do is you go down the left side, okay, and you see it says z 0, 0.1, 0.2, 0.3, 0.4, down to 2.0, okay? Now, in our case, what's going to happen is we're in this very first column because we are 2.0. If you had been like 2.01, 2.02, you'd have to go to the second column, third column, fourth column, depending on what you were at. But we are 2.0. You notice that the first column is labeled 0, right? And so what we find there is that this apple, what does it say down there? Yeah, it does say 9772. Thank goodness, I thought I made a mistake. It says 0.9772. Okay? And so this is a proportion. It's saying 97% of scores, 97.72, fall to the left of that point. In other words, this apple is larger than 97.72% of all of the apples in the world. Okay, so it's a pretty darn big apple, right? This apple is at the 97.72nd percentile, whatever the heck that means. Okay, so lots of ways to say it. But when I get a piece of information about the 97.72th percentile, whatever that is, then I can say the entire distribution equals 100%, right? And so if I know for a fact that 90%, 97.72%, fall to the left of 2.0, I can then say 2.28% fall to the right of that point. In other words, I can say two things. 97.72% of apples will be smaller than this one. 2.28% of apples will be larger than this one. Okay? Let's make absolutely positive. 97.72 plus 2.28 equals 100%. Okay? So that's where the 2.28 comes from. The 100, the total amount. Okay? And let's give the kid his due. Hi there, smiley boy. Okay. There you go. So now let's do the same thing with the orange. Okay, the orange had a z-score of negative 0.5. So again, we're going to go down the left side, and here's the deal: this chart only gives you positive z-scores. But remember what we have talked about already. The left and the right side are mirror images. It's the exact same story. Okay? And so what we find when we look it up is 0.6915. Okay? 0.6915. And what we find is when you were on the positive side, the number that was in this chart was literally the percentile. Okay, literally the percentile. But now all of a sudden, it's not. It's different. It's the opposite. Okay, so if you take that, what is it, 0.6915, and subtract it from 1.0, you get 0.3085. Okay, in fact, whoa. Let me see. Let me try this once. Okay, let me see this. Ready? 0.3915. 0.3915. That was my number, right? I better actually get that number before I look like an idiot, huh? It was, 0.6915. You see, it's probably a good thing I didn't do that. 0.6915. Okay. You looking? 695. Shitty marker. 0. The z-score I have is negative 0.5. Right? And when I looked it up in the chart, 0.6915 came out. Can you even see that? I need a better marker, maybe, huh? 0.6915, okay? And so now, what happened is that 0.6915, right, was actually this. This area right here in this curve, we see that. Oh, you can see that. All right. This whole area from negative 0.5 over is 0.6915. Huh? But what that means is this area must be, what is this now? 0.3085. What is that? Where the hell did I get 0.30? 1.0 minus 0.6915, because 1.0 or 100%, yeah, it's kind of a little off the edge. So together it must equal 1.0. What you looked up was and so we could say, you know what, this orange falls at the 30.85th percentile, or this orange is larger than 30.85% of oranges, okay? And so if I was to just grab an orange at random, 69.15% of the oranges would be larger than this orange. So just looking up that one number in this z-score chart, and I got all of these other pieces of information falling out of it, okay? So don't forget that this chart will only tell you this one piece of information. And your job is to realize that once you have this one piece of information, all kinds of other pieces of information are available to you. And so you need to take this one piece of information and figure out what question are they asking you. Which piece of information do you need to calculate? Where am I at? Okay? All right, so let's try some examples here, okay? I've got like 3 or 4 here that I've detailed very, very well, I hope. I mean, I put all this together last night, so I hope it looks good. If exam scores are normally distributed with a mean of 56.8 and a standard deviation of 8.14, what is the probability of selecting one score from the population that is less than 62? Wow, okay, that's a lot of words. First, we're going to convert the raw score to a z-score, because like we said, if you want to know probability, okay, where did it go? Here, look at this. Look at the top, I'm looking at the top line. I have a raw score in this example. I would like to know probability, or here it says percentile, but you know, probability, same ballpark. And so look at that. What I'm going to do is I'm going to take my raw score, use the z-score formula in the top left to calculate a z-score, and once I have calculated a z-score, I'm going to go to my table and turn that z-score into a probability. Okay? So that's the steps I'm going to do. First, I'm going to convert the raw score to a z-score. Okay? Here it is. So here's my 2 knowns in the top left corner. The mean is 56.8. The standard deviation is 8.14. Those are the givens. Now the score we have is 62. Okay? So I'm going to look at the z-score equation here. 62, which is my score, minus the sample mean of 56.8 divided by the sample standard deviation of 8.14. You do the math on it, and you get 0.64. Okay? So, 0.64. So now the question is not, okay, just a minute ago it was like, what is the probability of selecting a score from the population that is less than 62? Okay. Now the question that I've created a z-score becomes, what is the probability of getting a z-score less than 0.64? Okay, so I changed the question here, right? I could change the question from raw scores to z-scores. So now I can look up 0.64. So let's pull up, whoa, here, I bet you here it is, right? Bad boy, there you are, okay. So take a look at the z-score chart, okay? I want to look up 0.64, positive 0.64. And so what I find is I go down left side until I get 0.6, but I don't want 0.6, I want 0.64. So now I have to go, the first column is 0.60, the second column is 0.61, 0.62, 0.63, aha! The intersection of 0.6 and 0.04, I find 0.7389, okay? And so with this 0.7389, so what I have here, okay? So in the first little image on the bottom left-ish side, you see where 0.64 falls in the distribution. Now, what I looked up in the chart there, the 0.64, corresponds to 0.7389. And so you see here in this upper right-ish distribution that what that one number tells me is that 73.89% of the scores are at that point or below. We could say this score is the z-score of 0.64 is at the 73rd.89th percentile or something like that. And so going back to the question, we could find out it was asking us what is the probability. And so we could say the probability of getting a score less than 62 is 73.89%, okay? Which is literally this number. So this is a beautiful image, but here is an even more beautiful thing. Take a look at the bottom right image. And you see what we have there is there's my 0.64, and then I've mapped out the 0 in the middle, okay? The beautiful thing is now that I know that one piece of information, 0.7389, you see what I've been able to do is break the chart into 3 chunks, okay? Number one, like we said, if 0.7389 is to the left of 0.64, then the opposite, 0.2611 or 26.11% must fall to the right, okay? It must, because together it must be 100, 1%, 100% or 1.0 or however you're going to work with it. And at the same time, if 0.7389 falls to the left of 0.64, then because we know the properties of this distribution and how 50% must fall to the left and 50% must fall to the right of 0, and so all of a sudden 0.7389 minus the 50% that's over to the far left, and you see I've got 3 points there, 3 chunks I have broken this distribution into based on knowing one piece of information. So 0.7389 tells me, well, there's 50% to the left of 0, there's 23.89% between 0 and my z-score of 0.64, and there's 26.11% to the right of that. So one number, 3 pieces of information. All kinds of stories can be told here. Okay, good stories, good stories. Ooh, no, I have you done. Okay, I'm moving my stuff down. Okay, where is it? There it is. Okay, so let's try another one. A lot of words here, but you know what? You know how to pause the video if you need to. So if IQ scores are normally distributed with a mean of 100 and a sigma of 15, what is the probability of selecting one score that is greater than 123? Wow, that's a big number. So again, we need to first convert the raw score into a z-score. And so then let's do that. So let's convert the raw score to a z-score. Okay, again, in the top left corner are my 2 known pieces of information. The mu of this distribution is 100, the sigma is 15. Okay, I want to know the raw score of 123. So I will take those 3 numbers, the raw score of 123, the mu of 100, the sigma of 15, and convert that and create 1.53. Okay, so 123 minus 100, take that and divide it by 15, and you get 1.53. Beautiful. So now, I'm going to take that 1.53 and look this up into my z-score chart. Okay, I go down the left side until I get to 1.5. And so the first column, like we said, is 1.50, 1.51, 1.52. Aha! 0.9376 corresponds with 1.53. So I can take that information, that 1.53, and just like in the last example, it tells me 1.53, there's 0.9370 to the right. Left, to the left, to the left. Whoops, whoops, whoops. Now that I know that 0.9370, it does tell me that there are 3, this one piece of information becomes 3. Okay? Again, 50% falls to the left of the 0. 0.4370 falls between 1.53 and the mean. And remember, I got this 0.4370 by taking the original 0.9370 and subtracting 0.5. Huh? And then these 0.063 on the other side is simply the remainder, right? So, there I go. And so 1.0 minus 0.937 equals 0.063. Okay, so we hopefully got an idea where I'm getting these numbers from, right? Our understanding of the z-scores. No, here. Okay, so going back to remembering what the question is, what is the probability of selecting a score that is greater than 123? Looking at this image, which piece of information is it looking for? It's looking for greater than. In other words, it's that 0.063 that becomes an important piece of information to answer this particular question. Okay, where is it now? And so the question was probability. So we would look it up, figure out the 0.063, and then say the probability, if you went and just randomly grabbed a score from this distribution, the probability of getting a score of 123 or higher is only 6.3%. Okay? Sweet. Sweet, sweet. Okay, now we're going to have some fun. Are you ready for some fun? We're going to do a reverse question. Ooh, reverse. Ew. Forward was hard enough, but here we go. The height of a class of second graders is normally distributed with a mean of 123.4 and a standard deviation of 16.3. One child is told that their height falls at the 88th percentile. How tall is that kid? What? Yeah. Okay. Let me. Oh, I get in trouble here, but I'm doing it. I can do this. I can do this. Where is it? Where is it? There's the important one. Okay. If we know percentile, the kid's at the 88th percentile, and we want to find out the raw score. Yeah, how tall is this kid? You take the percentile. We're going to go to the z-score chart and find the corresponding z-scores. And then we will use this other equation to take the z-score and convert it back to a raw score. Okay, so that's what we're going to do. That one. Okay, 88th percentile. So now we need to go into the chart first. And we need to do something strange. We need to start looking for 0.88. Okay, we got to find a 0.88 in here somewhere. Okay, and so we're looking around 0.5, 0.50, blah, blah, blah. And we find that there is no 0.88 per se. Okay, but you see what we've got here is two numbers that are straddling 0.88. We've got a 0.879 and a 0.881. And so these are pretty darn close. Well, let's take a look at these. We find, what row am I in there? What is that a 1 point? I can't read that far. Wait a minute. 1 point. You little poopy. Yeah, it's a 1.1 row, right? 1.1 row. You can see it better than I can, I bet. What did I just say? Oh, yeah. Okay, good. It is 1.1. Okay, we're in the 1.1 row, and the answer that we want is somewhere between the 0.07 and the 0.08 column, okay? Because neither one is exactly correct, okay? So what we're going to do is split the difference and say the score, a z-score of 1.175 in between these two, 1.175, corresponds to the 88th percentile, okay? And so at a z-score of, what is it? 1.175, okay? At a z-score of 1.175, bad one. Okay. Are you watching? Okay, it goes like this. Z-score of 1.175. 88% of scores fall in that direction. Okay? That's what we just looked up. That is the information that we got out of the chart. 88% fall to the left of 1.175. 1.175 is at the 88th percentile. Okay, 88th percentile. Beautiful. Okay. All right. So now that we know the 88th percentile correspond. Oh, you little poop. Okay. I didn't say poop. What am I doing? Now I totally lost myself because it moved on me. There it is. Okay. Now that I know that 1.175 is the 88th percentile, we can take this other equation that we haven't used yet, but it's not hard. It's not hard at all. It's pieces of information. So we take the known mean of 123.4, the known standard deviation of 16.3. We shove in the z-score we just figured out, 1.175. And so in this equation, we got x equals 123.4 plus 1.175 times 16.3. Do the math on it, and we find out the child who was told they were at the 88th percentile is 142.5525 centimeters tall. Okay? What a beautiful thing. Okay? I can go from raw scores to z-scores to percentiles, from percentiles to z-scores to raw scores. Okay? I'm just going in opposite direction on this one. Okay, let's try this again. I know this is easy, right? Yeah, easy, my butt. All right. No problem. On an exam with normally distributed scores, the mean is 81.34 and the standard deviation is 12.41. So now this professor wants to grade on a funky curve. Are you ready? We're going to give this top 25% of scores are going to get an A. The next 25 are going to get a B. The next 25 are going to get a C, and the bottom 25 are going to get a D. All right? I was like, wow, that's kind of a brutal grading curve. But you know what? We're just going to run with it. Okay? So what's going to happen here is let's take this distribution. Number one, take a look at the very top left corner. Okay? Remember, we know that at a z-score of 0, 50 falls to the left and 50 falls to the right. Okay? Perfect. Now what we're going to need, though, is you move down one distribution to the middle left column, middle one, and what you see is that what we ultimately want to do is break up this normal distribution into 4 chunks, each one having a size 0.25. Okay, and so that's beautiful. Now, we know for a fact, again, you know, the middle division is going to be 0, have a z-score of 0. It has to, right? That middle one. And we know that the other 2 divisions on the far left and the far right of it must be the same z-scores, but one positive, one negative. Okay, because that's the nature of this distribution. So now, let's move it down to the left side, again, left column, very bottom image. Okay? And you see what we've got there is that when we want to break up this distribution, we literally need to have the point that breaks up, you know, that separates 75-25, because that's what we're going to find on our charts. Because what it always shows us is, so this 0.75 becomes the important piece of information to look up in the chart. So let's find the 0.75 in our chart here. Okay, and again, we have to go just manually start searching through all of these digits, and it's a pain, but they go in order, so it's not like random. And so you got to go start searching and look at what we find. Okay, just like before, there is no perfect 0.75. So you're going to have to start to find numbers around 0.75. And what I find here is a 0.7486, which is too low, and a 0.7517, which is too high. But it's pretty close to the middle between these two. Just like before, it pretty much splits the difference. So we're going to find this is in the row for z-score of 0.6. Okay, you look on the left side column, and you find it's at 0.6. And you come over, and you find that it's somewhere between the 0.07 and the 0.08 column. Put that together and get 0.675. Huh? So it's somewhere between 0.67 and somewhere between 0.67 and 0.68. We'll say 0.675. So you see here 0.675 on the left column, bottom image, 0.675 separates the bottom 75 from the top 25. Okay? And so, as I told you, bringing it back to this idea of, the 25 in each division. So, if we looked up the positive 0.675, negative 0.675 has to be the other one. That's the very nature of z-score distributions. These are the opposites. Lovely. So now what I've got is the z-scores that are going to break it up. So in that top group, people are going to get an A, in the second and the third and the fourth, etc. The grades are going to get. So now the question is, what scores should we be using? So we're going to take our equation, okay? Again, top left corner, the known pieces of information. The exam has an average of 81.34 with a standard deviation of 12.41. Okay, so the 25th percentile, or that bottom 25%, we're going to calculate it and say, okay, the z-score that corresponds with the 25th percentile was negative 0.675. We'll pull out our equation and plug in the numbers, a mean of 81.34, a standard z-score of negative 0.675, a standard deviation of 12.41, and say the raw score is 72.96. Sweet. Look at where I'm putting it on the distribution underneath that one break there. Okay? So if a student scores below 72.96, they get a D. Okay, sweet. The 50th percentile corresponds always to a z-score of 0. And you can do the math on it if you really want to plug it into the equation. Feel free. But the fact is, the 50th percentile will always be the mean. Right? It's just going to be, and I mean, look, if I put it in there, you see what the 0 does, right? It doesn't change anything. So it's the mean. So the second cutoff is, in fact, the mean, 81.34. And then the 75th percentile, we'll do it again, but now with a positive 0.675. And so, the sample average plus the z-score times the standard deviation equals 89.72. And so now I've got the 3 scores necessary to answer the question, which is, if a student scores between 72.96 and 81.34, they get a C. If they score between 81.34 and 89.72, they get a B. If they score higher than 89.72, they get an A. Okay? So I've broken up this distribution into the 25th, the four different breakdowns and converted it back into a raw scores. Beautiful. Okay, guess what? You can rewind if you need to see that again. Okay, that's a beautiful thing. So now, check this out. The normal curve, try this one. If IQ scores are normally distributed with a mu of 100 and a sigma of 15, what is the probability of selecting a sample of 4 scores from the population that have a mean greater than 123? Okay? Wow. We don't know how to do that. Okay? So we are stopping on that today. Today's material is to figure out how to work with z-scores for a single raw score. Okay? When we come back, we will talk about z-scores for a sample of scores. But that's a different game. We're not touching this today. Okay? So why don't you go back and run through those things and try to get a handle on them. All right? See you later.